So we're going to look at what matrix is, just a sort of general explanation of what it is I'm talking about. Then we're going to go through in some detail how to use the protocol to send a message. Matrix can be used for sort of instant messaging. So we're going to look at the JSON that you send and receive in some detail. Then we're going to look at the specifics of that JSON and how it's structured and what the different parts mean. In particular, the JSON you get back from the server. Then we're going to look at all the other types of events that you can receive other than messages. Then we're going to have a sort of an interlude into why it's interesting and difficult to write a matrix server. The protocol is kind of designed to make it easy to write a client, and therefore all the interesting stuff happens on the server. So we'll look at one of the interesting bits. And then we'll have a look at the much wider applications you can use matrix for other than instant messaging. So first of all, what is matrix? Well, it's a chat protocol. So what you can see on the screen is lots of different instant messaging programs designed for people with different tastes or different workflows. That all these people using these clients can speak to each other freely via an open standard because they're all talking matrix. So here's some examples of more instant messaging style clients, all developed by different people independently and interoperating. But you can also use matrix for more of a sort of group chat, IRC style conversations. There's lots of clients that support that way of working as well. Again, all over the same protocol, all end-to-end encrypted, or potentially end-to-end encrypted. But matrix is also an ecosystem of companies, governments, organizations that are building on the protocol, building on the software, building their own software to interoperate with it, embedding matrix in other things like a healthcare application or something like that. So there's lots of independent people working on it. So it is like a sort of grown-up open standard. One of the other cool things about matrix is it has bridges. So the fact that a logo appears on the screen means that at some point someone wrote a bridge to this protocol. Whether they're all working right now, I couldn't tell you. But it built into the way matrix thinks about the world is it doesn't try to have control over everything that's going on. So in contrast to some of the sort of disconnected instant messaging apps you might be familiar with, matrix is built to interoperate not only with other matrix servers and matrix users, but also with other protocols and other parts of the universe. So bridges are kind of built in. So I can talk to my friends who are unfortunate enough to be using WhatsApp using a matrix client going via a bridge. And also bots, which are great fun. So there's hundreds, maybe thousands of different bots that you can interact with on matrix networks to do all these kinds of things, interacting with social media, with code repositories, bringing up comics from some kind of comic website, calculating things, giving you the result back, tracking whether you did something good or bad, and giving you karma for that, sending messages through other systems like SMS, or even rendering some maths, giving you back an image, telling you what the weather is, all kinds of things. So there's a large number of people who are using the openness of this network to hook in bots. So that was kind of my introduction to what matrix is, but this is what the matrix.org website says matrix is. It's an open network for secure, decentralized communication, and that actually gives us a little hook we can use to try and open up a little bit of what matrix is. So first and probably most importantly, matrix is open. It's an open standard. It has a process for how you propose changes to that standard. There's a spec which you can read. You can also read all the proposals for changes to the spec on an open GitHub repository. Lots of things about the development of Matrix are open. Lots of the code is open source. Almost all of the code that my company Element writes for Matrix is open source and available on GitHub. And it's also open because it uses kind of well understood technologies. So you send and receive bits of JSON over HTTP. It's also secure. Matrix has the option for any of your one-to-one or group chats to be end-to-end encrypted using the double ratchet mechanism and extending that for group chat with a system called MEG-OLM. The security implementations have been publicly audited, and you can find the results of those audits. And it's also trying to define the extensions to the double ratchet extension mechanism into a standard that others can build on as well as being used within Matrix, which is this decentralized MLS thing. And it's also decentralized. And this is where it gets interesting and difficult and harder to implement and harder to standardize and think about because it's federated. So if you think about a system like IRC, you're free to run your own IRC server, but if you're talking to people on that server, you can't talk to people on another IRC server. So the difference with Matrix is if you run a Matrix server, you can choose, if you want to connect that Matrix server to other Matrix servers, and then the people who connect to your server can talk to the people who connect to that server. So the way to think about this is like email. If you have an email address, you can email anyone, and anyone can email you, even though you might own the infrastructure that you're using to send and receive email. So this means that anyone can run a server, which we tend to call home servers, but you can talk to people on the others. And actually, it's the combination of being decentralized and the security features that really give you sort of a high level of security. Because if you're an organization that really cares about keeping your communications within your control, you can run your own server, and messages between people on that server will never leave your data center or your infrastructure. But then you can choose if you want to. You don't have to, but if you choose to connect that server to others, then only the messages where you're talking to the people on other servers will leave your data center. So you can have complete control over the security. You don't need to trust someone else who may be in another country, another jurisdiction, to keep your stuff private. So let's get into some code, because that was a little bit too much waffle. So I'm going to show you in as much detail as I can what I did when I ran a server on my machine and then created users, sent some messages. So I did a git checkout of the code for Synapse, which is one of the most used home servers for Matrix. And then I did a couple of things with the config file, and then I ran this command, and then Synapse was running on my machine. So the first thing I did was ask Synapse what versions of the Matrix protocol it supported. So you can see it's listening on port 8008 by default. And a lot of the URLs all the URLs that we're going to see in this talk start with _matrix/client, because this is the API for a Matrix client. And then we just say versions, and we get back a bit of JSON that describes what versions of the protocol are available. Latest version at the moment is 1.2, which this server supports. So first thing we need to do if we're going to send some messages is register a user. So we go to the URL for registering. I've messed up that because that's version R0, which is still supported by this server, but I was doing this on version 1, so that should say V1 instead of R0. Anyway, you go to the URL where to register, and the first thing you do is just send an empty bit of JSON so that the server can tell you what types of registration it supports. And you can see in the flows section, it supports sort of what it calls dummy registration. So this is just running on my local machine. So we don't need to do anything clever with validating that you have an email address or something else you might do with a public server. It really tries to dissuade you from running a public server that allows open registration without any checking, because people who sign up on that server can spam anyone. So we need to put some barriers in their way to reduce the possibility of spam. But once we know what types of registration are supported, we can choose one, and we've chosen this dummy registration. So we send this little bit of JSON to the register endpoint, saying what type of authorized authentication I want to do, or what type of registration, I guess, which is dummy, and then just supplying what the username and password I want to use. And the response you can see at the bottom tells you your matrix ID. So under user ID, that string, which begins with an @ and has a colon in the middle, is a matrix ID. So my matrix ID is @andybalaam:/matrix.org. So if you want to chat to me, you can do it there. Because we're running this server on localhost, the server part of the name after the colon is localhost. So what comes back there is, so we've made a new user, here's their matrix ID, but also included in that is an access token that you can use to do more stuff. And also an ID for this device. And one of the nice features of Matrix is that it properly supports multiple devices, which is a surprisingly difficult thing to do, especially in a federated system. But you can log in with another device and still see all of your historical messages. Okay, so now we've created a user, let's log in. So first of all, we send nothing to this login endpoint, and it just tells us what types of login this server supports. And one of those types is password login, which is what we're going to use. So let's log in. So we send a bit of JSON saying what type of login, which is password login, and then we provide our username, which is that whole matrix ID beginning with that, and the password. And the response includes an access token, which is what we're going to use for all of our further communication with the server. And you see the device ID is in there again. So now we've got our access token. So just as a brief interlude, we'll register another user. So this is user 2, because in order to send a message, we're going to need a user to send and a user to receive. So back to the first user, we're going to create a room. So everything in Matrix really is based on rooms. Even things that are not to do with instant messaging, everything gets grouped within a room. So basically, when you join a room, that's when you sign up to receive anything that gets sent there. So it's kind of the unit of grouping of communication. We go to the create room endpoint, and we provide, there's quite a bit of optional stuff, but we're just providing this invite bit, which says which users we want to invite to this room initially. And the response comes back giving us a room ID. So that's how we're going to refer to this room in future. Just as an aside, rooms can also have aliases, which are like human-readable names for them. But the home server will have this sort of canonical name for a room. And it's your choice whether you decide to give them some other name. Okay, so now we get to the normal way that a client would be interacting with a server most of the time, which is by syncing, which essentially means asking the server, tell me what's happened since the last time I asked, or in this case, tell me what's happened ever, because we haven't said anything about what we've seen already. So we just say sync, do a GET request, and what we get back is a whole list of everything that happened that we might be interested in. So the first part, this next batch thing, is our way later we're going to say, I've already seen some of the stuff you might tell me, so only tell me the new stuff. So that we store that ID away so we can use it later. And then the interesting things that have happened so far on this server is that we are in a room. So in the room section of the response JSON, you can see the word join. And what that means, as far as I understand it, is this is all the rooms that you have joined. And then inside there's a map of room ID to some information about the room. And the way that most things work in Matrix is that all the information that you might want to gather is built up by a number of separate events. So even things like the name of the room or something like that doesn't come back as just a piece of information. It comes back as an event where this room got named, and then you can gather that together into information. So in this case, the first event we're looking at is the fact that this room got created. And that's basically, there are other events in there, but that's the interesting bit. So then if we want to sync again, like I was saying, we've now been given that ID that we can use to say where to start. And that means that we'll only be given back events that happened, or information that's changed since that sync token. So we're passing that in this since parameter, and we get back another batch number, which is almost the same as the previous batch number, but one number different, which is how we know it's updated. And so we did that immediately after the previous sync, so actually nothing interesting has happened. And this is a long poll, if we want it to be, so it will sit waiting until the server will kind of hold your request open until it has something interesting to tell you. Okay, so let's switch over to our second user that we created, and let's sync as that user, and hopefully we'll find the invitation that was sent to us. So the way you can tell I'm now user 2 is because the authorization header that I'm providing is using the auth token that I was given for user 2. So that may not be particularly obvious, but we're now user 2 because that token starts with ABC. So this user hasn't synced before, so they're going to get back a whole load of stuff from the server. And the bit we're interested in is if we look inside the rooms section, invite is the list of rooms that we've been invited to. So before we saw a list of rooms that we've joined, but for this user, we haven't joined this room yet, we've just been invited. And there's a bit more information inside there about what the invitation says, and what the state of the room is, which includes the fact that the room got created. Okay, so some more stuff comes back. So this is the other events that happened in that room that we've been invited to. So this event says that this room has a member, and it gives their matrix ID. So this is user 1. So it's basically saying you've been invited to a room. Here's some information about the room. One piece of information is one of the members is user 1. And also one of the potential members is user 2, which is us. And our membership is invite. So we've been invited, but we haven't yet joined. So this event was sent by user 1 because they invited us, but it's talking about user 2. So you'll notice that when I was creating the room, I didn't send this event to the server. I just sent a request to create a room, and the server created multiple events in response to that. So there's not a one-to-one correspondence between what we send up and what comes back down later. So the other thing we can do as user 2 is we can use this joined rooms endpoint, which kind of adds up the information that's contained in those events and gives us a convenient list of all the rooms that we're currently joined. So if you're implementing a client, you want a list of what rooms you're in, you might well use this endpoint to figure that out rather than kind of retrofitting it from all those events. So because we haven't joined this room yet, we've just been invited, there's nothing in our list of joined rooms. So let's accept the invite. So we go to the rooms endpoint and provide the room ID and then /join at the end of it. And I'm fairly sure I also had to include the room ID in the JSON that I sent, which is a sort of a repetition, but I'm fairly sure if I missed if I missed that out, it didn't work. But the response you get back is just telling you again, reminding you again of the room ID, but actually in the background, by hitting that endpoint and doing a post, you have successfully joined. So now we can ask which rooms we've joined. And instead of that, the response being an empty list, it now contains the ID of this room. So we've joined a room. We've created 2 users, created a room, joined a room as the other user. We're almost ready to send a message. So first of all, let's sync as user 2. So this is the second time we sync, so we're going to provide one of these sync tokens so we don't get all the messages again. But now if we look inside that room section, we now have a join section to tell us about rooms that we've joined. And within that room ID, we get the information about that room that we've joined. So switching back to user 1, which you can tell obviously from the auth token being different, we can sync again and ask what events have happened in this room. And we've now got a member event for this user 2 inside that room. So that user is now a member of that room. So if you were implementing a client, you would be keeping an eye on things like this so that you could display who's a member of this room and who's just been invited to this room. So we are now there. We are going to say something. So we're back to being user 1. We're going to go to this endpoint inside rooms, and then the room ID, and then send, and then you want to put the type of message that you're sending. So in this case, the type is m.room.message. And then you provide a transaction ID. So this is a put request. And we want it to be idempotent so that if something goes wrong, we can repeat the request and it will still work. So we make up a transaction ID as the client, which should be unique within any other messages that we've sent. It doesn't need to be unique globally or anything like that. And that means if something goes wrong with this request, we can just repeat it. Or if we think something might have gone wrong with this request, we can just repeat it, and the server will know that we're not sending another message, we're just repeating the same one. And then in the body of our request, we actually say what we want to say, which is hello from curl. And we give this message type to say what type of message we're sending. Provide our authorization token as normal. And the server responds telling us the event ID. So it's essentially saying, yes, I did create an event. And the ID of it, which you can use to refer to it later, is this thing starting with $. So we've successfully added an event to that list of events we were getting back when we synced. So now if we switch to user 2, and we say sync again, and we provide the right sync token so we only get new events, we can see in our timeline for this room, we have a new event which contains the message that we sent. So this is the fundamental process of one user sends a message and another user receives a message. Of course, in the background, what could be, and it's not happening in this case, but what could be happening is that you sent this message to one server and it jumped all over the internet in order to get to someone else's server and then get sent back to them. But as you can see, from the client point of view, the client doesn't have to know anything about that. It just turns up in that list of events. And then the client can render this in an instant messaging window. So yeah, as I mentioned, sync is a long poll, and you can provide a timeout parameter to your request. So if nothing interesting has happened for you, that request will just sit open for as long as you asked for. And then when the server has something for you, the request will end and you'll get back some JSON. So you're expected to just keep on polling and waiting. Whenever something happens, you show it to your user. Like this. So we sent another message, we sat waiting, and then it came through. So that was my way of proving to you that it really is just JSON and HTTP, and there's no magic. There is a bit of magic when you encrypt messages because you have to do some maths to decide what JSON to send, which I don't understand. But you're still sending HTTP requests with JSON in them. It's just that the server can't read them, but you've done some negotiations so the person you're sending them to can, or the people you're sending them to, which is particularly interesting, by the way. The people who are in the room can read your messages and no one else can. But then if someone joins later, they can read the newer messages but not the older ones, unless your room settings say that you're allowed to read the history in this room. So it does get interesting. Okay, so as we've probably picked up from this, messages that you send are events. An event is essentially a thing that's in this list called the timeline, which is stuff that's happened. And what we were sending, when we were sending JSON to the server, becomes what we call the content. So as you can see here, when you get stuff back from the server, you get a lot more than the content. But when you were sending that event, you just sent the content. And what the server adds is various pieces of information, including like a timestamp of when it received it. But you can't really trust that because you don't know whether you can trust other, if you're getting messages from some other server, they might just be lying about those timestamps. So we try not to rely on the timestamps. But yeah, an event gets an ID, and it gets the matrix ID of the sender of that message and a few other bits of metadata. The type of that message, of that event, sorry, was in the URL that we used to create the event, if you remember. So what goes in that content varies between different types of events and also can vary within these message events. So you're allowed to put in an HTML alternative description of your message. You should also include the plain text body, but you're allowed to put in things of different types, and you have to say the format in the format parameter, but you can put in this formatted body, which I believe is technically not, no, I think it is, no, it is in the standard, even though it has a slightly odd format name. Yeah, so you can have richly formatted messages. By the way, there are all kinds of other messages you can send, like images and stickers and stuff like that, but that would be a different message type. This is within the standard message type. And then here's a glimpse into the potential future. Maybe messages will begin looking more like this. This is currently being proposed as an extension to the standard to allow messages to have what's possibly a more sort of extendable structure. So notice the types changed from, what was it? m.room.message to m.message. But the key thing here is that within that m.message property inside the content, you can have multiple different MIME types of content. The other part of this extension is that you might have alternative ways of representing your message. So alongside the m.message property inside content, you might have m.image or some other alternative way of expressing this information. So that's a proposal to change the spec called extensible events, which confused me so much that I wrote a blog post about it, which you can read. Generally, if something, you can tell when I found something difficult to understand because I wrote a blog post about it. Okay, so that was message events, but there are other types of event that you need to be able to deal with if you're going to implement a client, including state events, which basically tell you information that is kind of true, not just something that happened at a particular time, but something that you need to know kind of all the time. And then ephemeral events, which are things that happen and they kind of, if they pass you by, you don't really mind. And probably some others. But let's not talk about how much I don't know. Okay, so here are some types of message events. So normal messages like we've seen, reactions where you can sort of thumbs up a message or something like that. And then just to take an example of something that's not standardized, we'll look at polls, but there are kind of hundreds of other types of message events. So we've already seen normal messages. Yeah. Yeah. Sorry, I misread my own slide. Yes, sorry. You can have reactions, but yeah, what I'm going to talk about is redactions. Thank you very much, which is it's kind of deleting a message. We'll get to that. Yeah, we've already seen normal messages, and we've seen what they look like. So thank you. Yeah, redactions are an event that you send to say, please delete the content of another event. And obviously, you can only do this if you have the right permission. So you generally do have permission to redact your own events. And as a moderator, you'll have permission to redact other people's events. The reason why it's called redaction as opposed to deletion or removal or something like that is that the way these events work in the kind of data model on the server, which we'll see a bit later on, is a kind of tree of events that point at something that happened in the past. So we can't just randomly delete things from that tree, or our tree will become a forest, which will confuse us. So what you can do is just say delete the content parts of this event, but the kind of the metadata of it still continues to exist. And generally, the server, well-behaved servers will actually delete the content, so it's really gone. But the nature of federation is you don't know what other people's servers are actually doing, so you can never be 100% sure that something is gone, but this is kind of the best we can do. So you can see everything happens within a room, so you've got the room ID in there, and you've got a record of like who redacted this event. Okay, so on to polls, which is something I've been working on reasonably recently. A poll is what you would expect from polls in social media or something like that. It asks a question and allows people to respond. There are a number of events involved in that, so I'm only showing you the event that lets you start a poll. But the type there is org.matrix.msc3381.poll.start. So that is a unstable type prefix, which helps you know that this has not yet been standardized. This is a proposed standard proposal. So MSC stands for matrix spec change. So this is proposed. It's completely fine and normal to implement events that are not in the spec and use them. You just can't expect anyone else to know what you're talking about. So inside the content we have the question you want to ask and the possible answers. And then there are other types of events sent by other people to say, I'm voting this way in a poll. So as I was saying, this feature is unstable. It hasn't been accepted into the spec yet, but we've implemented it in our client, and that's allowed. It's not bad behavior on our part. I think it probably would be bad behavior to take something that kind of should be standard and not try and get it standardized. But part of the standardization process is saying there is an implementation of this and the spec does make sense. So it's completely normal to build an implementation and then say, look, community, do you think we should standardize this feature? You can follow that link to read the spec proposal. All of this is public, all the comments on it are public on GitHub. So the summary of what message events are is something that happened at a particular time. So another type of event is state events. And state events are things that you probably need to know right now rather than just when they happened in the past. So for example, the fact that a room exists or the creation of a room, the name of that room, and whether someone belongs to that room, which obviously changes over time. Lots of other state events. So to take an example, here's the event that you see when a room got created. Notice that it has a state key property, as well as that type saying it's a room creation event. Notice also there's a room version. So part of the spec process is that as we kind of learn more things about how to do this protocol in the right way, we need to change the rules about how to resolve just any number of things that might happen, like events that kind of contradict each other, or someone doing something they shouldn't be allowed to, or something like that. So when we realize we need to change the rules, we change the room version. So this is a room version 9. So if you create a room at version 9, then it will follow the rules for that. That's the rule set for this room. And if you don't like room version 9, you want to use room version 10 when it comes along, you need to essentially end that room and start a new room, which is at version 10. And there's a mechanism for saying, this room's finished and you should go here to find the continuation. Another example, you can state the name of a room. And again, notice that there is a state key property, but its value is empty, which seems a bit weird. And then when you're talking about who belongs to a room, who is joined in that room. Again, we have a state key, but this time there's something in the state key, which is the matrix ID of that person. The type is room.member. So the reason why those other events had a state key with an empty property is the fact that you have a state key, with an empty value, the fact that you have a state key is what says that this is a state event, and state events get handled differently. Essentially, the server keeps like a key value map of state key and type to value, which it can provide to you at any time, not just as events that happened at some point in the past, but when you ask about this room, give me the state of this room, it will give you all of that information, or the latest version of all of that information straight away. So by putting that state key in, we're saying, this is a state event, so I want you to include this when you give me the state of the room. Yeah, that's just repeating what I said. Okay, so another type of event I want to tell you about, ephemeral events. So ephemeral events happen, and you might see them, you might not, and you can live without seeing them. So one example is this user is typing, and that's something that happens inside a room. There are also ephemeral events that don't happen inside a room. For example, this user is online, which is called presence. Thing to note about ephemeral events, certainly that was surprising to me when I learned about it, is they don't have an event ID. So effectively, you can't kind of refer to them later. So they really are a sort of fire and forget thing, that you can't redact them. But yeah, I'm typing, so my client tells everyone in the room, Andy's typing, but if they missed that, well, no one cares. So one other possible use of ephemeral events is to gain a certain type of privacy. So something that we're looking at the moment is sharing your location and giving live updates of where I am at this moment. So we've already finished with a kind of static location share to say at this moment in time I was in this location, and that kind of is part of the history in the room that it seems okay from a privacy point of view that these people all had permission to see the messages that I'm sending. I want to tell them I'm here at this location at this time. It seems okay that they're able to access that data later, but it seems potentially a little bit too much to say the exact trace of my location over this longer period is all stored in the room history. You might want that if you're doing like a cycling tour and you want to show your route, you might want that, so we potentially might implement that. But you might also want a type of location sharing that is kind of visible to people who are online at the moment, but then later it's not locked into the history in this room. So we will probably be using ephemeral events to say, essentially say, I'm here now, but it won't kind of get written forever into the history in this room. Okay, so that was events and some types of events. So let's move on to what's interesting and fun and exciting about trying to write a server, a matrix server. And like I said before, because we really aim to make the life for the client author easy, life for the server author can get really hairy. And I'm only going to touch the surface of one of the bits of that hairiness. So the context for state resolution, the state resolution algorithm, which, by the way, we're on version 2 of, which is probably pretty good. Maybe there'll be state resolution algorithm version 3 at some point, but so far we're only on version 2. The context is that servers can get out of sync with each other because the internet connection between them was down, or because they were overloaded, so they weren't able to send messages back and forth between each other, or any number of other reasons. But two servers can disagree, and a sort of desirable property of the protocol is that at some point we want to come to agreement about what happened in this room. And in particular, if two servers have the same information as each other because they've caught up after some kind of split, we want them to agree. If they have the same data, they definitely should agree on what happened. And that's harder than you might think, especially because of things like you can't trust the timestamps and stuff like that. So you need to know which event came first, and especially you need to know whether this person sending this awful message happened before or after this person got banned from the room, something like that. So it's kind of important that we have a decent algorithm for choosing what happened before what. So here's like a really simple representation of how the server sees these events that we've been looking at. So we haven't seen it because as a client you don't see it, but each event has effectively a pointer to another event, which is the thing that happened before it. So it's a similar structure that you might have seen in other things, including like in a Git repository, each commit has like a pointer to the previous commit. So this is the kind of nice situation where everyone knows what happened before what. But when some kind of split happens, two servers may very well have a different idea of which event happened before which other event. So in general, a server will try and have just a linear history like this. It will build, every time something new happens, it will say the previous event was whatever my latest event is. So the two servers still have this kind of straightforward view of the world until they start talking to each other again after the split. And now suddenly they've given each other the information that was previously missing. And now they have this tree shape that's not just a straightforward line. We've got two events, one that was created on one of the servers and one that was created on the other, that both point at this oldest event as the thing that happened before me. So it's worth pointing out that this is fine, right? This is not a kind of a real problem like it would be in some system like a blockchain where you have to kind of figure out who's right and pick the right answer. In this case, we're totally fine with the fact that these two things both have the same event as their previous event. It's just that we have to figure out what happened in some sensible way. So this basically doesn't cause us any problems if these events don't actually conflict with each other anyway. We can just accept all the information we've been given about both. But here I've drawn on that A1 and B2 conflict with each other. So what I mean by conflict is they change one of the important pieces of state and they disagree about the answer. So one of them says this user was promoted to an administrator and the other one says this user was banned from the room or something that we need to know. There's some kind of conflict going on. So now we need to kick in the state resolution algorithm. So I should point out I'm skimming over quite a lot of details in the next few slides, partly because I don't fully understand it and partly because it's probably just too much to talk about. But yeah, and some of this description, I'm talking about all the events that happened, and in some of this description, I'm only talking about the important events, and exactly what I mean by important events is quite a complicated description, but basically you can think of it as, someone got banned and they also got promoted. Those are both important things. We need to figure out what happened. So we need to know what order did things happen in. So as soon as we have a linear order, we can process the events one by one, saying, oh, this person got banned, and then they promoted someone else, but they weren't allowed to do that because they'd already been banned. Right? So as long as we have an order, we can figure out the current state in the room. So the basics of how we figure out this ordering is using something called Kahn's algorithm, which, it's brilliant to give credit to Kahn for coming up with this algorithm, which I imagine was very difficult to figure out, but it's like blindingly obvious once you see it. So it sounds like we're sort of over, like trying to make ourselves look clever by giving the algorithm a name. I'm glad to credit this person. But essentially, what we do is we look at everything that doesn't have any arrows going into it, and we know that they're kind of like as new as you could possibly say, right? So A3 and B2 are new because no one has built on top of them. So we can stick them at the bottom and say, well, definitely the kind of latest thing that's happened is going to be either A3 or B2. And now once we've removed them from the graph, we just do it again. We just look for all the boxes that have no arrows pointing into them, and those must be the next newest things. By the way, you should definitely imagine a situation where there are a lot more boxes and arrows and a lot more forks and mess. So especially if a server's got overwhelmed at some point and has been failing to speak to other servers, there just could be chaos in this graph. So I've simplified it a lot. But the algorithm still works, right? Anything that's got no arrows pointing at it is new. So we can put that into the list. So we can take B1 and A2 and say the A3 and B2 are the newest, and then A2 and B1 are the next newest. And then we can take A1 and stick it at the top. So at that point, we finished using Kahn's algorithm, and Kahn's algorithm won't help us resolve which of these pairs is newer. So then we can switch to some matrix-specific logic. And the summary of the logic is, as I understand it, having read it last night, is whichever of these two events has the highest power level, which means the person who sent the event had a higher power level than the person who sent the other event at the time this happened. Power levels, by the way, are a number from 0 to 100 or possibly 1 to 100. And actually, I think it's not really defined. You can use any number, but the convention is we use numbers between 0 and 100. And you can assign that meaning yourself. So in a chat room, there's a fairly common convention that I think 50 means that you can modify other people's stuff, and 100 means you can kick anyone out. Or, I don't know. Anyway, there's conventions, but if you're using a room for a completely different purpose, like not chat, for example, you might have different conventions for those power levels, so it's left completely free. Anyway, point is, the first thing we look at is which of these two events had the highest power level. If those are equal, we might look at the server timestamp, even though, as I said, you can't necessarily trust that. But in this case, we're not trusting it. We're just using it to, in a predictable way, pick one of these two events. So it doesn't actually normally matter. Well, no, it doesn't matter because the power level thing will have resolved any kind of like abusive behavior that's happening here. So just by lying about your timestamp, you can't kind of cheat this algorithm. If the two events have the same timestamp, then we just use the event ID that they've been given and just like you just pick one because it's lower in the alphabet. But we've got some way of resolving which of these two events came first, which means that we end up with this linear order by just sorting those pairs out. So that's the kind of fun and exciting stuff you'll be doing if you're writing a matrix server. This is all in the spec, by the way. So there's very specific instructions about how to implement this version 2 of the state resolution algorithm. Much more specific and correct than what I just said. So yeah, as I said, the important outcome here is that if two servers have the same set of events, they should give the same result. Otherwise, the world is just going to be weird. If you're connecting to a different server, you're looking at the same room, but that room looks different, things are going to be weird. And I do think, much as I prefer to avoid talking about blockchains in any way, it is interesting to contrast this with blockchains. So blockchains have this similar idea of, like pointing back to the thing that happened before me, and this idea that two parts of the world might disagree on what the truth is about what happened. But in blockchains, it's like that's a disaster, and you need to fix it by throwing away one half of history. In Matrix, it's fine. It's designed to live in a world where there is incomplete connectivity, and we just merge it together later. And we're happy with that. Okay, so I said that Matrix was a distributed real-time database, and now I've just talked about instant messaging. So let's try and fulfill some of the promise there. In order to implement chat, I mean, this is arguable, right? Because XMPP is not a real-time distributed database. XMPP is a message passing system which successfully allows people to chat to each other, but there are features you don't get if you don't implement a distributed real-time database. So Matrix does implement a distributed real-time database, which means you get to receive messages even if you're not online, because when you come back online, the message has been stored and it gets delivered to you. Also, you can add another device later, and you can see the messages on that device. And you can scroll back through the history of a room, even before you joined it, if the rules of that room say so, and see what happens. So these are desirable features for some people when using chat. And in order to do that and do it in a federated way with multiple servers controlled by different people that talk to each other, you effectively need to implement a distributed real-time database. And what you get from that is that you can deal with servers appearing and disappearing and then filling in information later. You can be robust to the network going down, or even someone attacking the network, potentially. So we've ended up implementing a distributed real-time database. For example, Synapse, the server that I was talking about earlier, it's built on top of Postgres, or SQLite actually, but generally Postgres. But what it implements itself, or that whole network of servers, federated servers talking to each other, is a distributed real-time database, which is by which I basically mean there's lots of machines cooperating to share the truth with each other. They talk to each other quickly. When something happens, others hear about it quickly, by some definition of quickly, and the data is stored and can be retrieved. Okay, so it turns out, obviously, that a distributed real-time database is not just useful for chat, but also for loads of other interesting and exciting things. For example, setting up a video conference or a voice room where people join in and talk to each other while they're chatting. Also for collaborative document creation in any of the many different types of collaborative document. Also for what some people have been calling the metaverse, and some people have been avoiding calling metaverse, which I'm calling immersive environments. Also for peer-to-peer messaging that doesn't require a server. And it's important to know that actually the original creators of Matrix didn't particularly set out to design a chat system. They were actually interested in immersive environments or VR worlds. So it always had, chat was always just one of the purposes behind designing Matrix. It just happens to be one that is a really good test of it and really sorely needed in our current situation. So video conferencing. So you might ask, like, why do you need a real-time communication system to do video conferencing? We've already got WebRTC, which lets you connect up to another machine. But what's missing from the WebRTC standard is how do you negotiate? How do you decide who's calling whom? And if two people want to talk to each other, one of them has to call and one of them has to receive, and you need to negotiate all that stuff. And if there's multiple people in the room, you need to figure out like where they all are, who's calling whom, and stuff like that. So you need like a signaling layer. So you need some kind of real-time communication. Matrix is really well suited to do that. There is an MSc 3401. The link to which I assure you is in the slides. They're just off the bottom of the screen, which defines how to do it. And so I'm relatively new to Element. I only joined 6 months ago. And I would say I've been blown away by the ambition of the Matrix project. But in particular, I've been blown away by the ambition of this MSc 3401. What it defines is not just a way of setting up a video call. It's a way of setting up a video or voice call that is federated on some really deep level. So if you imagine one of the central servers like Jitsi or one of the other video conferencing servers, they're kind of like the IRC analogy I was giving earlier. You can run your own Jitsi server. People can connect to it. They can talk to each other, but they can't talk to people on other Jitsi servers. So MSC 3401 fixes that problem for like all the video servers out there. If they decide to talk this protocol, not only will you be able to connect to an individual and do a video call with them, which by the way you can do in Element right now, but also you'll be able to connect to your government's Jitsi server or your company's Jitsi server and still talk to people who are in a different government department on a different Jitsi server, because the two Jitsi servers will be talking to each other using MSC 3401. So it really fixes a sort of walled garden problem that we currently have if we can get people to use it. So yeah, we're currently looking at what type of SFU to build. An SFU is one of these sort of central units that you can connect to in order to do video conferencing with other people, and how to hook up those SFUs to each other. And anyone else who wants to interoperate with that network of people talking to each other can read the MSC and implement it, or other people can build that on top of the way they currently work. So that MSC is there and fairly mature. What's implemented already in a product called Element Call is using that protocol to negotiate between individuals in a room. So not this SFU part, not the Jitsi or other central server, which is in the spec but not yet implemented in Element Call. But in Element Call right now, you can go into a room, start a video call, it figures out who's calling whom and all that stuff, and you end up with like a full mesh peer-to-peer set of connections between the people in that room. So there's no other server involved. You've got end-to-end encrypted communication between you, and then each person's computer opens a call to each other person's computer, and you're all talking to each other with no one else in between. What that does mean is if you have too many people in the room, it doesn't work, because the reason why you need these central nodes is you don't want to open 200 WebRTC connections to people because you haven't got enough bandwidth for that. Yeah. Anyway, so this idea of not just having like one SFU, one focus point, but hooking up these so they can talk to each other, so they can, you have these kind of central nodes and then people connected to each of them, communicating between each other. It's kind of a mirror of the way Matrix thinks about the world, applied to video conferencing. It really fixes the kind of dual problem of wanting control of your own stuff, but also wanting to talk to other people. Okay, other stuff. So I mentioned collaborative creativity. So like the most used example of this would just be like Google Docs, right? Many people can work on a document at the same time. So there's some really relatively mature implementations of this on top of Matrix, like this whiteboard called the board. And then there's lots of really innovative new stuff that is not mature. So the Collabs library is a library that lets you build things like collaborative editors and a load of other stuff in quite a straightforward way. There's this project called Matrix CRDT. So you might have heard of CRDTs. They're a relatively new, I guess it's kind of a mathematical idea, but very practical. A CRDT is a system where you can have multiple people doing things, taking actions like deleting this letter or adding this word. A CRDT is a way of resolving those actions without ever hitting a conflict that needs some kind of intervention. So you'll always come to a decision. It may not always be a decision that all the users agree with. If one person's deleted a paragraph and the other person's modified that paragraph, someone might still be upset at the end of that. But a CRDT means that you will come to a decision without some kind of unresolvable conflict. So CRDTs are this idea that is relatively new. YJS is one implementation of CRDTs that is becoming pretty popular. And then Matrix CRDT builds support for YJS into Matrix protocol. So if you want to build a collaborative tool like maybe a diagramming tool or something else. If you use matrix CRDT, you will get the power of YJS, but you'll be able to use matrix to send and receive the edits that you're resolving. Does that make any sense? Okay. Do ask questions at any time. Other stuff you could do with it is you could have like a drive with files stored and then updates to those files. For that, you would use the kind of room mechanism. So, like I was saying before, rooms are kind of the fundamental unit of stuff in matrix. Like they're the groups of people who can talk to each other, but they're also like the unit of organization of stuff. So you might, for example, model a directory in your file system as a room, and you're allowed to have rooms inside rooms, so you can have like subdirectories and stuff like that. So. You probably wouldn't store the like contents of large binary files as events in matrix. There's like a limit on the size. Part of the matrix spec is like a file storage server that's used for things like sending images between users and stuff. So there is some kind of file storage already built in. What I'm talking about here is kind of a real-time visible file structure is what you would be storing in matrix, and then pointing at the contents of the file somewhere else. So in terms of immersive environments, there are prototypes running right now. There's this thing called Third Room, and there's a link to a YouTube video of it, and this is moving really fast, so probably this is out of date, and you should just search for Third Room with your favorite search engine. Third Room is this like virtual environment where you can interact with people, and it does all of its stuff through Matrix, through the Matrix protocol. So like figuring out where the other person is and showing them all comes through Matrix. So you get all the cool stuff that you get with Matrix kind of for free. Like end-to-end encryption is there, and federating, talking to people who are on a completely different server. And once you've kind of met up in a room, your two computers can then be talking directly to each other to make this virtual world where you can interact with people. This is like, in a way, this is a little bit too exciting for me to have an exciting slide about it, because the prototypes are kind of moving fast, and amazingly cool stuff is going to happen really soon, but I haven't got any screenshots of it yet. So I think, there are metaverse skeptics and there are metaverse enthusiasts, and I would see myself as a skeptic. And then I started to see some of this stuff happening and started to think, actually, maybe we're going to spend like 12 hours a day in these environments pretty soon. Maybe, hopefully not. Another exciting thing that's happening right now is peer-to-peer stuff. So if you're in a situation where you don't have the internet, or the internet is controlled by someone who's trying to stop you doing what you're doing right now, you're probably interested in like Bluetooth-powered peer-to-peer networks. So it would be really cool if you could talk to your Matrix friends, especially if you were organizing a protest or something like that, without needing to trust the internet, and also without needing to rely on the internet being there. Or you want to talk to people who are on the internet, but you're not on the internet, but there's a chain of peer-to-peer nodes that will eventually hook up with the internet. So this is a really active area of research, including some people from, or driven, I'd say, by some people from Element working on it. So effectively, the way that we make Matrix peer-to-peer, in a way, is very straightforward. You just put the server on your phone, and we've got a server that we've been working on called Dendrite, which is pretty lightweight and can run on your phone. So that sounds simple, but in actual fact, the hard bit is like how to decide which devices you route through so that your message gets to where it goes. So that's like an active area of research, but doing extremely well. So coming soon is, there's no longer a server involved, or actually it's on your phone, but you don't know that. So you don't need to trust anyone else's server, and you can keep talking to people just because your phones are nearby. Which, if you think about it in a certain way, like, why didn't we have this as soon as phones existed, right? But sometimes takes us a long time to get round to stuff that should have been there in the first place. So that was your introduction to what Matrix is, how to write a client, kind of some of the interesting stuff, and then some of the cool stuff that's happening right now. So thank you very much. So I'd recommend, have a look at matrix.org and also read this blog post, the Mega Matrix Holiday Special 2021, which is just this enormous list of all the amazing stuff that's happening in Matrix right now. Any questions?
When is this, when do you expect the on-full options?
The peer-to-peer. Yeah, so the question is when will the peer-to-peer stuff be available? So there are prototypes at the moment. I think the work that I've seen, I'm not deeply involved in it, but the work that I've seen is currently about the routing part of it. So they've been writing a routing algorithm which seems to outperform some of the other peer-to-peer routing algorithms that already exist. So I think that blog post predicts that there'll be some usable peer-to-peer this year, but that I would call that a prediction rather than a promise. But yeah, it would be cool. Other questions? Right, well, thanks again for dragging yourself out of bed. And I'm happy to chat afterwards. Bye.